Compounding data rarely lies, and when R&D teams review the final stability assays for a new peptide formulation, the numbers usually tell a frustrating story. A high-end, clinically proven anti-aging active, purchased at an enormous premium, has become completely inert inside the final emulsion. These formulas almost never fail because the peptide itself is ineffective. They fail because the formulation environment actively destroys the molecule long before it touches human skin. Our efficacy trajectory starts at 98% in vitro, plummeting to 12% in formulation as variables are introduced. The instinct is to increase parts per million based on claims, but adding more active to a hostile base is the concentration fallacy, multiplying cost without stopping degradation.
OnlyTRAININGS. Learn what works in the industry.
Biomimetic and natural peptides are structurally sensitive and function-specific. Because natural peptides are derived from biological sources, they carry inherent molecular variability that makes their three-dimensional integrity even harder to maintain. Achieving true efficacy requires rigorous architectural integrity of the formula itself, not just blindly increasing the dosage of the active. Supplier efficacy claims are typically generated in neat solutions, controlled in vitro environments with ideal pH and zero competing chemicals. A cosmetic base, however, is a violent reality. It introduces shear stress during mixing, hostile pH shifts, and aggressive preservative systems. This split screen shows the consequence. On the left, a stable, folded peptide in isolated water. On the right, it rapidly unfolds and breaks apart, bombarded by surfactants. This gap between the pristine petri dish and chaotic compounding vat is where formulations fail and budgets are wasted. Formulators must actively engineer the environment to protect the peptide from these specific threats. Translating in vitro claims into real-world performance requires treating the formulation base as a life support system for the active. Saving a formula requires a systematic approach. We start with the risk to mitigation framework, beginning with the first major threat, degradation. For natural and synthetic peptides, hydrolysis is the primary structural threat. Even minor fluctuations outside a peptide's narrow, optimal pH window act as an immediate trigger for this hydrolytic breakdown. This is compounded by a secondary degradation pathway, metal catalyzed instability, caused by trace elements introduced during the compounding process. This flowchart tracks the combined breakdown. Step 1. Fluctuating pH destabilizes the peptide bonds. Step 2. Trace metal ions attach, initiating rapid oxidation. The exact mitigation strategy involves mapping strict pH limits before compounding begins and utilizing strategic antioxidant pairing to intercept oxidation. This mitigation is most critical during the temperature drop in the emulsion cooldown phase, where thermal stress often finalizes the degradation. Ignoring water activity levels over the product's intended shelf life will also result in continuous slow-motion failure. Preventing structural degradation requires preemptive environmental controls mapped during R&D, rather than relying on post-formulation pH adjusters. The second major threat in the framework is compatibility conflicts with other ingredients in complex systems. We map this using a hidden formulation risk map, where trusted, standard base ingredients secretly sabotage sensitive actives. Ionic clashes are particularly dangerous. Integrating cationic, positively charged peptides into bases heavily reliant on anionic emulsifiers virtually guarantees chemical failure. This is the macro-level manifestation of a severe chemical incompatibility in a finished formula, separating into grainy, discolored precipitants. This physical precipitation means the peptide has completely bound to the emulsifier, resulting in a total loss of biological function. Interactions with standard preservative systems and electrolytes will similarly cause unexpected viscosity drops or discoloration. Mitigation requires instituting mandatory charge compatibility checks and running pilot interaction tests before formal stability testing begins. Unmapped chemical interactions destroy the peptide's biological function. These oversights convert expensive functional ingredients into inert, destabilizing debris. The third and final framework step is delivery and bioavailability reality. Advanced formulators must work within a central biological constraint, the Dalton limit. Large, complex natural peptides cannot passively penetrate the hostile barrier of the stratum corneum, regardless of how stable they remain in the jar. Without assistance, the raw peptide molecule simply bounces off the surface of the stratum corneum. An encapsulated version of the same peptide, however, successfully slips through into the dermal layer. Overcoming this barrier requires aligning the active's molecular weight with the overarching formulation architecture. This requires selecting advanced delivery systems, utilizing specific encapsulation approaches, and carefully balancing penetration enhancers. A perfectly stable peptide is utterly useless if the formulation's delivery system leaves it stranded on top of the skin. Formulation is a commercial reality. R&D teams must make highly informed decisions on which actives to purchase and use. You have to separate raw supplier marketing claims from decision-grade evaluation, data based exclusively on your actual intended formulation environment. This radar chart demonstrates how to mathematically evaluate an active's viability across multiple constraints, plotting cost per kilo against stability thresholds and required penetration depth. True cost-to-performance optimization involves balancing these three factors to deliver measurable results without over-engineering the system. Because natural peptides exhibit significant batch-to-batch variability due to their biological origins, chemists must implement standardized analytical controls. Simply increasing the concentration to compensate for inconsistent raw material is a costly, ineffective strategy. Commercial viability requires chemists to critically interpret technical data and set concentration thresholds based on formulation realities, not brochures. To solve these specific challenges, we created the Precision Peptide Formulation, Stability and Performance Strategies online training. This course provides advanced troubleshooting frameworks, hidden interaction risk maps, and ready-to-use reference formulations. Mastering these strategies prevents formulation failures, eliminates costly redevelopment cycles, and ensures compliance. Transform fragile, unpredictable actives into reliable, commercially viable products that perform precisely as designed under real manufacturing and shelf life conditions.